Good morning, everyone. I'm going to be going over Chapter 9. I hope everybody's doing okay. And I hope that my modules are helping, and I guess you guys are learning something in some way. So Chapter 9 is everything to do with the hydrosphere. Remember, in the beginning of the semester, we looked at the Earth and we divided it in different spheres, right? You had the lithosphere, hydrosphere, atmosphere, biosphere, and then the cryosphere. So today we're going to be looking at the cryosphere and hydrosphere. Next week we're going to be looking at the biosphere, which is really cool. We're going to be looking at plants and animals and biomes and things like that. So let's get started. So we know that water is essential to life. It's distributed unevenly on, in, and above the earth. So most of our moisture is going to be stored in oceans, lakes, and streams, right? And we kind of divide the water based on salt water versus fresh water. Obviously, salt water is ocean water, right? There are rivers and lakes that are also considered salt water. And fresh water is really important because that is what is available for us to drink, right? Frozen water represents some of that water as well, and our frozen water is going to be fresh water. Frozen water represents about 3/4 of all the fresh water on the planet. So our hydrological system or hydrologic cycle has been seen as this series of storage areas, right? So either it's stored in the atmosphere, in the oceans, in the lakes, rivers, streams, frozen, right? They are interconnected by different transfer processes. So this entire system is going to be a closed and circular system. We're not gaining any new amount of water or losing any water, right? Everything that we have always had. Does that make sense? And the reason that there's kind of like this fight over water or this lack of water security is because we cannot rely on ocean water as our source for drinking water or water to irrigate our plants in agriculture, right? So there is such thing as desalination plants, but that takes a lot of energy, and there's a lot of consequences or negative impacts from those plants. So let's look at this picture here so you can kind of get an idea how much water we as humans have. So if you look at this large chart up here, you have 97.2% of all water is in the ocean, and then 2.8% is fresh water. This is what we need here, okay? This is what we have to drink. Cool, 2.8%. Of that 2.8%, almost all of it is frozen, right? It's in glaciers. And then only this much is really available to us. 0.62% of it is in groundwater, which we still drink, but most of it is underground. And we cannot rely on that for a source of fresh water because you cannot extract that groundwater completely or quickly, because then you have a lot of issues on land. So, you know, look at that small sliver that is available for us to drink of all that fresh water. Only this much is really what we rely on, which is not very much, right? Here's just another picture of what that looks like. Most water is in the ocean. Some sources will tell you 98% is ocean water, 2% is fresh water. Yeah, that's about right, right? And of that fresh water, 2% is frozen. So about 0.5% fresh water is available for us. So now you start to understand why there really is kind of like this unequal, there's not really great equality in access to such a necessary resource, right? And how do you add a value to something that should be free for everyone. You know what I mean? So that's really difficult. And the way our water is spread out, our fresh water is spread out across the world, is not even, right? So you have very, very dry areas in North Africa and Southwest Asia. And then you have areas like Canada that their water per capita is extremely high. They have way too much water. So it just comes down to that. Here is our hydrologic cycle, which we learned about very well in chapter 6, right? So precipitation obviously happens over oceans, winds move those clouds over land, and then you have rainfall, precipitation, you have runoff, surface runoff. Some of it goes into our rivers, lakes, and streams, fills up our reservoirs, and then if not, it goes back into the ocean or in this underground collection of water, which we call groundwater. Movement on and beneath Earth's surface, you have surface water and groundwater. Surface water is just what it sounds like, right? It's water that is found on Earth's surface in streams, rivers, lakes, ponds, reservoirs. Groundwater refers to underground water in the subsurface zone where pore spaces are completely filled with water. So it really depends on the geological makeup of the area. You have some soil or some rocks that are more porous, and they're able to suck up, or really to get filled with more water than other areas. Underground water reappears at surface via springs. So there are places where underground water or groundwater naturally flows up, and those are called artesian wells. And the city of Artesia is named Artesia for that reason. So along Artesia, Compton, Bellflower, there is a large aquifer. I think it's called the Artesian Aquifer. I might be wrong, but that used to be a place with a lot of farmland and agriculture because there was natural springs there. So that's why Artesia is called Artesia. Pretty neat. So here is a picture of this groundwater, right? So you can have different places that those aquifers do fill up. And so you would have a water table. So you have like clay, and that does not allow water to seep any lower. So water starts to fill up. And then you would have this area here, which would be your kind of your confined aquifer, this area here. So it's just underground water, right? And it fills up. And then the place that it comes up to, you would call that the water table. That's all you need to know about groundwater. I'm not going to get into it too much. I took a whole semester on that, and it was the most exciting semester I've ever taken. You notice the excitement in my voice? Yeah. Earth contains underground formations that collect and store water. These are called aquifers. Water percolates and seeps underground through cracks and spaces in gravel and sand. It's important for you guys to understand that, you know, it's not just what we see on the surface, right? Groundwater is very important. It provides drinking water or fresh water to many, many communities around the world. I don't know exactly the percentage, but they do get a good amount of their water from an aquifer. So it is very important. Here's just another picture. Here's the artesian well where you can just use that water underground. It'll come up, right? Here's the water table. That's the area or the place, the zone that water reaches to the top or stops. This would be a confined aquifer that it's stuck between two impermeable layers, but this is filled up with water, and this would be an unconfined aquifer. All right. And if you do use that water too quickly or suck it out too much, you do get this kind of cone of depression and it can lead to other things like land subsidence. So because the land is on top of that aquifer, if you deplete that aquifer too quickly, or you take out that water too quickly, the land starts to sink and drop. Okay, let's get into our oceans. This is really what I want to get to in this chapter. Where did our ocean or our ocean water come from? Rain, right? Maybe rain, but where did that rain evaporate from? So it's kind of like what came first, right? There's many different theories on this. One theory is that there is a huge frozen comet or meteor that hit the earth and gave us half of our water. And then a lot of it began before there was water on the planet. There were volcanoes, and volcanoes release steam. And so that gave us our first rainfall, and that's kind of where it came from. So it's still left up in the air and left to theory, but a lot of the information we know about our oceans, we've learned in the past 60 years, and 60 years is not a long time, right? I know it sounds like a long time, but it's geologically and scientifically, it's not very, very long. It's pretty new. A lot of our ocean life is still unknown to science. So we're still learning a lot about the ocean and the depths of the ocean. So not until 1950 did we have the sophisticated equipment to catalog and measure the details of our underwater environment. So that's why there's a lot of portion of our oceanic life that is still unknown. I mean, before we thought that our ocean was kind of like this vast abyss, like flat. There was nothing going on. But when we did start going deeper and having those submarines to look at the ocean, we noticed that there were underwater mountain chains, underwater volcanoes, trenches, all these different things going on. So that's actually new in the scientific world. How many oceans do we have? Most of you would say 4, right? Or 7. Yeah, you're probably right, but there's actually one world ocean, right? It is all interconnected, and all those names of those oceans that we've learned since we were kids are just kind of for us to have more of a geographical sense of what we're looking at, right? So you have the South Pacific Ocean, the Pacific Ocean, North Atlantic Ocean, the Atlantic Ocean, the Indian Ocean, the Arctic Ocean, the Southern Ocean, which I learned when I was a kid, it was the Antarctic Ocean. But I'm looking at the map I have in my home right now, and it says the Southern Ocean. So we have very many different oceans, right? 3/4 of Earth's surface is covered with water. We're known as the blue planet. And that's what makes us so unique, right? In this galaxy, anyway. So it's Pacific, Atlantic, Indian. Here's a picture of those. The largest ocean is the Pacific Ocean. And I hope most of you guys do know that the coast that we live on is the Pacific Ocean coast. You'd be surprised how many people do not know that. Here's just a picture of our oceans and different seas. So you have the East China Sea, the Bering Sea, Gulf of Mexico, Hudson Bay, all these different areas, the Mediterranean Sea. It's still all part of one world ocean. Movement of ocean waters. There are many different ways that the ocean begins to move. Because the ocean is liquid, it is in continuous motion, and this motion can be grouped under 3 headings: tides, currents, and waves. The movement of anything over the surface, like wind, boats, swimmers, it can all set water surface into motion. So the ocean surface is always rigid with swells and waves. And also disturbances of ocean floor can cause significant movements in water. Chapter 14 will look at how tsunamis can move ocean waters, or underwater earthquakes can cause tsunamis. The gravitational attraction of the moon and the sun causes some of the greatest movements of all, which are tides. So we're going to look at tides and currents today. Tides are primarily vertical motions of water. They're caused by a gravitational attraction between the moon and the earth. And also there are solar tides. So there's solar tides and lunar tides, but lunar tides are 2 times as strong. The causes of tides: the earth exerts an attractive force on the moon, and the moon also exerts an attractive force. It's kind of like 2 magnets pulling at each other, right? It is the gravitational attraction between the moon and the earth that causes tides. So if you can imagine, like the moon, even if it's much smaller, it's still pulling at the earth, but it's not really going to pull, right? So you have the earth here, then you have the moon. The earth is surrounded by, it's enveloped by water, right? This is very exaggerated. But because the moon is pulling at the earth is not really moving at it, but it causes the ocean kind of to bulge like that. So this would be like a higher tide here because the moon is pulling at that. And then ocean currents. I'm going to spend a little more time on these ocean currents. There's 2 types of currents. You have surface currents and deep ocean currents. Okay, so surface currents are caused by wind flow. So remember chapter 5, we learned about the trade winds, the subtropical highs, right? Those were those constant bands of high pressure, low pressure, trade winds, southeast trade winds. You had the westerlies, right? All those winds cause the ocean to move. So these are surface currents caused by wind flow. They're referred to as subtropical gyres. So remember, you have the earth, right? 0 degrees, you have low pressure. You have 30 degrees, which is high pressure. In these high pressure areas, you have air that is diverging, descending at the surface, right? So when this happens over water, over ocean, it kind of causes this to happen, right? So at these areas, you have these subtropical gyres because the earth, because the earth is spinning, it causes kind of like this toilet bowl effect, and everything that is in the ocean ends up floating into this area. So let's look at this. So you have your subtropical high, right? This is about 30 degrees, right? And then you have all kind of like everything that's in the ocean ends up here. So everything that's in the ocean is going to end up in this area. And what I'm getting to is that Great Pacific Garbage Patch. You guys have probably heard of it. It's an island of trash the size of Texas. It's not technically this island of trash, but it is an area. There's 2 areas where everything that is floating in the ocean kind of ends up. It's kind of like this sink, this drainage area. So anything that's in the ocean, whether it be natural debris or what do you think is in the ocean? A lot of plastic, right? So all that plastic ends up into this area, which we call the Great Pacific Garbage Patch. And you do have these islands here. Obviously, you have the Hawaiian Islands. You have an island called Midway Island, where it kind of is just in the middle of all that plastic trash. And so much plastic ends up on that Midway Island. And you have a lot of wildlife that ends up eating that plastic. So the Great Pacific Garbage Patch, this is not a picture of the Great Pacific Garbage Patch. This is a picture of a river in India, but I think I just put that up because this is what people imagine it to look like. And it technically doesn't look like this. A lot of the plastic that ends up in this area has photodegraded or degraded over time. So if you can imagine, if you've ever seen, if you've ever left a water bottle in the sun for a long time and it kind of turns really, really hard, and it breaks down into a bunch of little pieces. That's kind of what's going on with a lot of the plastics in the ocean. It reacts with UV radiation, and it gets really, really tough, and it breaks down in tiny, tiny little shards. And so in the ocean, you don't have these large, plastic bottles. You have these tiny, tiny broken down pieces of plastic, which is even more harmful. So these are called microplastics. Most trash sinks, some trash sinks, but most floats. There are two main regions. You have the eastern garbage patch and the western garbage patch. So this is Midway Island. This is a little bit before you get to Hawaii, and this is where all the trash ends up. And they have to take hundreds and hundreds of pounds of tons of garbage off of this island every 3 months. Like, they just have to do it. And these little albatrosses, or these birds, birds are not the smartest animal in the world. They just eat whatever they find. And these birds, they die because of what they are ingesting. So this is just a picture of what is in the belly of these birds. So this is what it would look like. These are microplastics, and they end up bioaccumulating in our food, right? So at the very top of the food chain is us. So we are ingesting a lot of this. Some sources say that even sea salt has traces of bisphenol A, which is a component of plastic. So it is extremely pervasive and prolific in our oceans. I don't know what the answer to this is, but I mean, this is every piece of plastic ever created is still on the planet, And so something that is also adding to this are these microbeads that are purposely made for our beauty products. So if you have any of these products that are exfoliants, they are made up of tiny, tiny little plastic beads, which our water systems our water systems and our drains are not created to catch these. So they go straight into the ocean as well. So that's adding another problem to something that is still like this problem we cannot even fix. So if you do have any type of exfoliant that has made up out of little plastic beads, and you'll know because on the back it'll say polyurethane or poly something, you also don't want to be scrubbing your face with plastic, right? So try to replace those with a natural exfoliant, and you'll know because it'll say, okay, you can use this every 3 days. These plastic exfoliants, you're able to use them every day. So try to think about that in the future. How long till it's gone? These are estimated decomposition rates of common marine debris items. So an aluminum can takes about 200 years to decompose. I don't want to say biodegrade. An apple core, 2 months. A plastic bottle, 450 years. Fishing line is a huge issue because a lot of these fishing companies, they'll leave the lines out if they get tangled or if they get caught in something. And that is a big problem in the ocean. Styrofoam cups are 50 years. Styrofoam is like I don't want to say the worst, but it is one of the worst things for the planet. The production of styrofoam and the actual styrofoam itself is tremendously harmful to our environment. So there's that. And here's this picture. I just thought it was really important and relevant to what we're talking about, right? And I will have some videos and discussions to do with this topic. Okay, so those are ocean currents, right? Upper ocean currents. Now we also have these deep ocean currents. They're caused in deep ocean at very, very deep levels, and it's because of differences in water and water salinity and temperature content. So some water is saltier, and saltier water, is heavier, so that will sink. cold water is heavier, so that will sink. Your deep ocean circulation is a system of deep ocean circulation that happens because of differences in water density that arise from differences in salinity and temperature. Ocean water will become denser, and so it'll sink, and if its salinity increases or temperature decreases, that adds to the density and it starts to sink. This causes your thermohaline circulation. It is a circulation of deep ocean water occurring because of differences in salinity and temperature. They start at high latitude areas. So this red line here, these are surface currents, and the blue line are deep ocean currents, right? So once the surface water gets to these high latitudes, it gets colder, and so it sinks, right? And it follows this. This thermohaline circulation is a circulation of deep ocean water occurring because of differences in temperature and salinity. So thermo, temperature, haline, salinity, thermohaline circulation. The circulation plays a huge role in energy transfer around the globe. Research suggests that there is connections between our global conveyor belt, or this thermohaline circulation, and global climate. So it doesn't really play an effect on immediate weather, but it does play effect on climate. Remember, climate is long-term weather, like 30 years of data, right? Where weather, like your localized weather system, it wouldn't really play an effect on that. But overall global climate, it would. So here's just that entire thermohaline currents. And if you've ever seen Finding Nemo, you know, that stoner turtle, Crush, he's like riding the EAC, bro. He's riding the East Australian current. I don't know if it really looks like that, but there is an East Australian current, and it's like around here. So, and I honestly don't know if turtles really use the current. That's actually something I should look up. Yeah, but that's pretty cool. I love Finding Nemo. So it's our deep ocean conveyor. It starts in the North Atlantic, where cold, dense water sinks and slowly flows deep below the ocean to the south. It eventually joins the eastward, moving deep, cold, high salinity water around Antarctica. Okay, let's get into the cryosphere. So the cryosphere is our frozen portion of the hydrosphere. It is second only to the world ocean as a storage reservoir. So most of our water is in the ocean, right? Most of it. But the second largest reservoir or storage of water would be our frozen portion. There's still a lot of water that is frozen. Even if we're quickly losing we're losing glaciers very, very quickly, right? I think you guys watched Greenland is Melting last week, and just to give you an idea of how quickly we're losing our frozen portion of the hydrosphere. The cryosphere is the ice part of the hydrosphere. It's divided between ice on land and floating ice. Ice on land is much larger. Here are some definitions of floating ice or ice formations. So this one here is going to be an ice pack. This is going to be an ice shelf. This is an ice floe. And this is an iceberg. And so I'll have these slides without my narration up on Canvas as well, so you guys can look at that. Glacial ice covers about 10% of the Earth's surface. All the dark blue is where we still have glaciers, right? Just a little bit here. So, as I was saying, South America has you have glaciers in Africa, the Himalayas. Greenland is one of our largest glaciers that is quickly disappearing, as we saw in that video. So this is where most of our glaciers are. They cover about 10% of Earth's surface. Recently, formerly stable ice shelves have broken apart. So like the North Pole, for for example, used to be unnavigable, but now we're seeing that that ice is melting quicker than before, and it is not like ice like it used to be. Now it's kind of like this slushy type of material, so it is opening trade routes from Russia to North America, or whatever, to Canada, whatever the case is. Russia is claiming that this will be their ocean, so they have already set up a command post here, and they are banking on climate change to completely open up this ocean here, which is interesting to me. Antarctica has quickly lost their ice sheet, so this is the approximate extent of ice pack at annual maximum is out here, right? So these are like seasonal changes. Permafrost is another important portion of the cryosphere. So this is permanently frozen subsoil. So if you look at this picture here, you know soil carries a lot of moisture with it, but in high latitude places, so we're looking at 60 degrees or higher, right, in terms of latitude, like Canada, Alaska, Russia, all these places, their subsoil is frozen, so we call that permafrost. It's widespread in northern Canada, Alaska, Siberia. Because of our changing climate and warming global temperatures, that permafrost is beginning to melt quicker than before, and so it leads to a lot of issues. Within that permafrost, there are tiny trapped bubbles of methane. So anytime you have like dead organic material, like dead plants, dead animals, the bacteria that decomposes that, anything that is decomposed, it releases methane, right? It digests it and releases methane. So that methane is trapped within that permafrost because it's frozen, it cannot be released. But because that permafrost is melting, that methane is now being released into the atmosphere. So methane is a greenhouse gas, it's a climate changing gas, and it is 23 times more potent than CO2. So one molecule of methane into the atmosphere is like 23 molecules of CO2. So now we have all this permafrost melting all over these northern latitudes. Now it's adding to the warming, which is going to cause more permafrost to melt, which is going to cause more methane to be released, which is then encourages more warming. So you see how this is a positive feedback effect, right? One change incurs another change. So it's kind of like this runaway effect. We haven't seen the true entire extent of climate change quite yet. So that's just one example. Here is where some of our permafrost is located. In the dark blue, the higher the latitude, the more permafrost there is. Down into northern North America, that light purple, is less permafrost. So organic matter is decomposed by microorganisms, CO2 and methane is released. This increases the greenhouse effect, or greenhouse gases, which increases warming, which promotes more permafrost to melt, which is like this positive feedback effect, or this runaway effect. So I'll have videos linked on your modules, and you guys can answer some questions based on the permafrost melting situation. Also can lead to damages to buildings. So if that permafrost starts to liquefy and turns into water, if that permafrost melts, it does lead to land degradation, so buildings can be damaged. Water use and resource problems. When it comes to water use, we do not use it sustainably. We put a big amount of importance on agriculture and livestock. That is where most of our water goes to. So when someone talks about water use, things can have a certain water footprint, right? like to the shirt that you're wearing that has a water footprint. It takes so many gallons of water to create this cotton t-shirt or whatever it is that you're wearing. Even the food you're eating. Some food is water intensive, more water intensive than others, right? So you have to think of that food from the moment what it was before until the moment it got to your plate, right? You can attach a water footprint or a carbon footprint to pretty much anything, right? So for instance, beef. Beef is the greatest user of water in terms of any other animal protein. It takes a lot of water to raise cattle, to raise feed for cattle, and then finally for that beef or that burger to get to your plate. I think it's something like, I want to say 700 gallons. So depending on the product, like a burger, for example, it takes 200 or 2,400 liters of water for one hamburger, right? For a glass of beer, 75 liters. For a glass of milk, 200 liters of water. For coffee, for one cup of coffee, it takes 140 liters of water. So agriculture is the greatest user of water worldwide, which we know, right? Obviously, you need water to grow food, but you have to think of the type of food that you're growing. Some foods are more water intensive. And where are we growing and raising these types of animals, right? And can we live without it? Is it necessary? So there will be a video for you guys to watch on this, and it's a very important portion of the surface waters. So these are just water bodies that are on the surface of Earth, right? Like a lake, a pond. A lake is a body of water surrounded by land, and a pond is just a very small lake. There's no scientific difference. This picture here is a picture of Lake Baikal, which is found in Russia. It is the world's largest freshwater lake. And what's interesting about this freshwater lake is it's the only place on Earth that you find these little freshwater seals. Look how chubby they are. Aren't they cute? Only place on Earth you find a freshwater seal. All seals are saltwater, right? So they don't know, but they think when this lake was being formed, somehow a seal got in and evolved and was able to survive within this freshwater. So they are characterized by being very, very round, and they swim very fast. They're called the Nerpa seal. Saltwater lakes or saline lakes, more than 40% of the lake water of the planet is salty. One example is the Great Salt Lake in Utah. The formation of lakes, two things are necessary. Obviously, you need a natural basin with a restricted outlet, and you need sufficient inflow of water to keep this basin partially filled. And this picture here is a picture of Convict Lake. Actually, I took that in 2010. And the book, it's interesting, has a picture of Convict Lake as an example of a glacier lake. So this lake is filled by snow, and it was carved out by the movement of glaciers. This is found in Northern California in the Eastern Sierras. If you took your field trip already with Crystal Lovatier, you probably went here. It's absolutely breathtaking, really, really pretty. I think this is it for today. Yeah, and this is just another picture of the Convict Lake. So just finish your modules, and there will be some videos and questions attached. I did make this chapter very, very quick because I'm noticing a lot of people are not really watching the entire video, which I understand, right? All right, you guys take care, stay safe, and I will talk to you guys soon.